Yeah, so thanks a lot, Chris, for the introduction. Thanks for the organizers for inviting me here. It's been a very nice conference. I've learned a lot of things, and given the title, you might expect that I've learned a lot of things because I am not from group theory. And so I'm going to be talking about some joint work with William Cunningham, Dimitri Piyukov, Gabor Lipner, and Garlo Tugenberger. And I guess, I mean, given that we've all had dinner last night, it was very nice. And I heard some people actually stayed all the way till closing time, right? So I'm very happy that you're here now. But it also feels that I'm sort of obliged to somehow, yeah, try to convince you why you should stay here at this moment, because the title of the talk doesn't have anything in it that relates to group theory, right? So why would this be interesting to you? So, well, the first thing is that I'm going to be talking about a way to infer geometric features on discrete structures. So there's geometry in there. This is something that I've seen many people are very interested in here. And in particular, the discrete structures I'm going to consider are graphs. So you can also think of Cayley graphs associated to groups, but actually the method that I'm going to show actually is applicable to sort of any reasonable metric space. So you can also just think of your favorite group with your favorite metric on it. So then I've also covered maybe some group theory. And in particular, what I'm going to show is that this inference measure, right, that has some way of measuring curvature of spaces, that it actually converges to the right answer in the infinite size limit of my graph. So there's some asymptotic analysis as well. And I hope that by the end of the talk, somebody can give me an application of this, because then I've covered all bases, right? So hopefully that will be the case. But at least I'm hoping that this will convince you to sort of stay in your seats for the next, say, 42 minutes. And I'm going to talk about how you can estimate Ollivier-Ricci curvature in random geometric graphs. Now, before I do that, I want to give you a slight introduction into the type of work that I do, because that will be sort of a motivation of why I'm actually interested in this type of question. So in general, the work that I do is I work on random graphs. And so random graphs are just some way of generating graphs that has some probabilistic flavor to it. And in particular, I really like models for random graphs that have some geometry in it. And so at a very cartoony level, what does that mean? It means that I'm going to start with some geometric space, and I'm going to envision the nodes of my graph sort of as being placed in this geometric space. And they can be either placed deterministically or according to some random process. And once I've placed these points in the metric space, I can also put additional features on it. I can make it as complicated as I want. Then I also have some sort of probabilistic rule that tells me when two nodes are going to be connected. And that has to do, for example, right, with the distance in the space that they have. And I can then sort of combine all of these things, and I get some graph out of this. And there, of course, the nice thing is that we can look at these methods in lots of different types of metric spaces. And so the most classical setting is where you just consider simple Euclidean space. And this is a very classical case called random geometric graphs. But you can make it more exotic. So you can also talk about random geometric graphs in hyperbolic space. Hyperbolic space is also something, or at least hyperbolic groups, hyperbolicity is something that I've also seen a lot here. And you can make it as more complicated as possible. You can put all additional features on nodes, and there are lots of ways to do it. What I do want to mention is that actually using sort of latent geometry to create sort of connections or graphs, it's not sort of something that mathematicians came up out of just all by themselves. I mean, the notion of a latent space and latent space models was already used in sociology and psychology long before, because these people already realized that if you want to understand how people relate to each other, or how that has to do with how close people are in some hidden space that tells you about how similar people are. So they already used these types of models, I guess not hyperbolic space models, but Euclidean space models, to study social behavior. But I'm using it to create graphs. And in particular, right, just to give you sort of a flavor, I want to sort of show you sort of an example of a model that has hyperbolic space. And that's also because I've seen that lots of people here like hyperbolic geometry. And in order to sort of explain to you this model, which is also going to be a motivation of the type of question that the talk will be about, so I have to set the stage. So I'm always thinking of hyperbolic space in terms of the Poincaré representation, which is, I think, also very, very standard here. I've seen many pictures that are basically Poincaré representation. So basically, I always like to show a picture like this, right? This is an Escher painting, right? This is called the circle limit 3. This is basically a tiling of the hyperbolic space in Poincaré representation. Now, the model that I'm going to describe, right, is going to be in what is called the native representation. So instead of just taking this open disk of radius 1, we're just going to map the open disk to the Euclidean plane. That's called the native representation. And you have to just then also do a transformation on your coordinates and on your distances. And if you do this, just to show you what happens, right? If you do this to the circle limit, then this is what a slab of that native representation looks like. So this is just because I'm going to show you some pictures, just to make sure that you understand this is not a picture on the Poincaré representation, but on the native representation. I'm just stretching the boundary to infinity. All right, so what is the model then? So the model was introduced by one of my collaborators, Dmitry Kryukov. It has several parameters. Most importantly is n, which is going to be the number of nodes in my graph, and Rn, which is going to be a connection radius. And so what you do is you, this native representation lives on the Euclidean plane now with the associated metric. So what I'm going to do is I'm going to sample points, which I'm going to represent in polar coordinates. And I'm going to sample them according to some probability density. The formulas here, don't look at it. I mean, you're allowed to look at it, but you don't have to remember it. It's basically sort of a quasi-uniform distribution on the hyperbolic space, tuned by the parameter alpha. And then what we're going to do is once the points have been sprinkled, we're going to connect 2 points if their hyperbolic distance is less than r. And in this native representation, we can get a formula for this using the hyperbolic cosine rule. And what we get is we're going to connect 2 points if their angular distance is less than this r cosine based on their radii. So it's just we sprinkle points in this hyperbolic plane and we connect 2 points if they are within distance Rn. So what does that look like? So here's an example. So what you see here is you see indeed that, as you might expect, if you sprinkle points uniformly at random, right, the further you go away from the origin, the more points you will see, right? That's how the metric works. And what I did here is I highlighted 1 point somewhere on the boundary, and the shaded area here is basically the ball. So these are all points in the space that satisfy this inequality. So these are all points that are distance Rn away from this point within this circle. And as you then move your point closer to the origin, you see that these often called lollipops, they increase, right? And they become bigger and bigger. And in particular, it means that nodes that are closer to the origin of your space, they will make more connections. So they will have a larger degree. And then if you then do the connections according to the rules, you get a graph that looks like this. So here you can already see there are some sort of almost tree-like structures, not exactly tree-like structures on the boundary. And in the middle, everything is starts getting connected to each other. But these are very nice models because, I mean, we can study them and we can prove lots of different types of properties of them. And this is what, in general, myself and people in my field like to do. So, for example, we can study the average degree. So just the degree of all nodes divided by the number of nodes. And you can then prove, this was done by Google Manifold in 2020, that indeed this average degree converges to some number. And that actually means that our graphs are sparse. So the number of edges is linear in the number of nodes. Now, what they also did is instead of looking at the average degree, you can also look at the distribution of the degrees. And you can also prove that that has a very nice, well-defined pointwise limit, which has a certain type of tail dependency, which we personally very much like in the random graph community. And recently, together with some other co-authors, we studied another property, which is the average number, the average fraction of triangles a node participates in. So you can look at a node, then you can look at any 2 neighbors of the node, and you can ask, well, are these 2 neighbors also connected, right? Do they form a triangle? And you can look at the fraction of those triangles. So the total number of triangles that the node can have is just its degree choose 2. You can look at the fraction of triangles each nodes have, and then you can take the average over all nodes. And we proved that this also converges to some limit. I don't want to show you the expression of this because it will take more than 1 slide. It contains basically all special functions that you can think of, but we have an exact expression for it. And there are lots of other things we can study for these graphs. So these graphs are well studied. Lots of people are very interested in this hyperbolic random graphs. We know things about the size of the giant components, uniqueness. We know things about the clique size, largest cliques. We know distances, even explosions, if that means something to you, right? We also know this and much more. So, yeah.
First, could you explain again how you generated distribution? So, I mean, you have the radius and the angle. So you had some slide a while back, and
So here, yeah.
What's happening in this formula?
Yeah, so what's happening in this formula
Sort of at a slightly higher level is this is a density, right? So it's a density on the polar coordinates, right? So I just sample my points according to this density. Okay, so how you can think of it, just what you can just think of it, I mean, forget about the alpha in the formula, just think, you take this disk of radius Rn in this native representation, sprinkle points uniformly at random, just n points uniformly at random. Rn is chosen in terms of the parameter, so Rn is 2 times the log of the number of nodes divided by this parameter nu. Yeah. But you can just think, I mean, just think of the points being sprinkled uniformly at random, or no, this is indeed, this is so there's this native representation here, and this is just a ball of radius Rn within this native representation. No, it's not a sphere, it's a ball. No, it's a surface, yeah. But the thing, right, so I wanted to show sort of this model to also give you some type of an idea of the type of sort of models that we're working with and sort of the type of geometry that we're working with.
Sorry.
Yeah.
Representation, that was also a little too fast. Is it conformal? What was the formula again?
No, it's not necessarily conformal, right? What you just do is you take the Poincare representation and you just map the boundary to infinity. You stretch it.
You had a specific formula.
Yeah, we had a very specific formula.
Why that formula, especially if it's not conformal, right?
No, it's just to make. I mean, it's to make the pictures nicer, right? So I can define the model in the Poincare representation, but then if I draw the graph, it will be you will not see too much, right? So I want to use the native representation just to give you a better view of the graph.
The ball is it's like a hyperbolic ball, and the function uniform and hyperbolic.
Yes, yeah.
But then your picture is. Yeah.
My picture is in this native representation. You can think of just a hyperbolic ball centered at the origin of the hyperbolic plane, right, in the Poincare representation. And then my nodes are uniformly sampled on this ball. And what I'm drawing is just I've mapped this ball using this native representation to the Euclidean. That is.
The rule for connecting two nodes for an eight was not again.
The rules just if their hyperbolic distance is less than this radius r. Yeah.
I mean, okay. So I just wanted to show you sort of this type of. So I'm very sorry if I confused it too much, right? Because this was really just sort of a motivation of the main question that we have here. Because the thing is that we know very well at this point, right, how to study the properties of graphs that live on certain geometric space. So for example, this model that I showed you, we know a lot about it. We can study a lot of properties of it. So we can go in this direction, start with some metric space, generate a graph, and study the properties of the graph. But the question that I really want to ask here is, what about the other direction? So suppose somebody generated the graph using some geometric space and some rules, and then they give you the graph, but they don't tell you anything about the metric space. They say, okay, here's the graph. Is it now possible for me to look at this graph in some way and extract information about the hidden underlying geometric space just from the discrete properties of the graph? Now, there are lots of reasons why you would like to do this. For example, in terms of model inference, right? So if I would be able to extract the type of geometric space, I can sort of infer the right model that was used. And once I infer a model, I can start doing lots of sort of applied things, right? I might even be able to, for every node, to sort of estimate where it lives in this space. And then I can do lots of things like designing efficient routing algorithms. I can predict missing links in the network. But the actual question that actually brought me to this problem was posed by theoretical physicists that were working on quantum gravity. Because there are, I mean, and I'm not an expert, right? So I can only tell you what they told me and up to the level that I understand. So there's one branch in theoretical physics where they're trying to solve this problem of quantum gravity. And in this branch, what they're really trying to understand is, well, you have this sort of quantized look of spacetime. So it's a discrete notion of spacetime. and you want to put some gravity on it. And gravity, as best as we know, it depends on geometric features, in particular on geometric features of continuous space. And so they said, well, they basically explained to us that, okay, they would really like to be able to start with some discrete structure, some quantized discrete structure on space-time, and then infer which sort of continuous geometric space is sort of underlying discrete structure. So basically they are asking this question. They say, I have some discrete structure where there might be some underlying hidden geometry, and we would like to understand this geometry, because once we understand this, we can do things that might bring us closer to solving this quantum gravity problem. This is what I know from what they actually do. But the question was very interesting. And so we said, okay, let's have a look. Let's see if we can do this. So, and in particular, right, so it's about extracting information about the geometry, right? So what is the sort of the key information you would like to know? It's curvature. Curvature is basically sort of the key fingerprint of your geometric space. And probably I don't have to explain to most of the people here what curvature is, right? Just sort of very simply how I also look at curvature, right? Curvature is some sort of general local notion that tells you how far away you are from Euclidean space. And so if you have zero curvature, you're flat locally, negative curvature, you're locally hyperbolic, and then positive curvature is locally spherical. And if you're talking about the setting of Riemannian manifolds, there are different ways, different notions of curvature, right? So you have sectional curvature, scalar curvature, Ricci curvature. And for this talk, I'm going to focus on Ricci curvature. Now, I'm not going to formally define Ricci curvature, because I mean, you can do this in terms of the Levi-Civita connection and everything, right? But for the purpose of the talk, that's not relevant. You can, I mean, there's going to be some notion of curvature. I can compute it, right? And it's called Ricci curvature. What I do want to sort of spend a bit of time on is some sort of high-level intuition on what Ricci curvature tells you about what happens to the volume of your balls if you do parallel transport. Because that's going to be, that intuition is going to be, well, that intuition turned out to be fundamental in constructing the right notion of discrete curvature. So let's just imagine your favorite sort of nice Riemannian manifold. We'll put a point x in it. We'll take a unit vector v. And then the idea here is that we can compute the Ricci curvature of at v, right, at x in the direction of v. And then we can relate this to how the volume of transported balls changes. So how can you look at this? So what you do is you walk a distance delta in the direction of v. So you walk a distance delta in the direction of v. You put another point y there. And then you consider a ball of a certain radius around x. And now what you're going to do is that for every point in the ball, you're going to parallel transport it in the direction of v to along a distance delta. Now, and then several things can happen. If you're in flat space, right? So if the let's say that the entire region of this balls is locally flat, right? This entire region is flat, then the volume is preserved, right? You just move at all points, volume of the balls are preserved. If the curvature is negative, what it basically means is that sort of at a high level, this volume of these balls grow when you start moving these points. And if your volume, if your curvature is positive, then the volume shrinks. And there's, of course, lots of caveats, lots of slightly technical details, right, if you really want to make this precise, but it's really about sort of this intuition. So if you look at a ball and you start parallel transporting, right, then the balls change. And the change of the ball depends on the curvature of your space. So it's this change of volumes of balls that led sort of to this idea of defining a certain discrete notion of curvature. And basically, from this, the main insight is that if you would like to develop a general or abstract definition of curvature, you basically need three things. You need some notion of a distance, of course. You need a way to measure the volume of a ball. And you need to be able to compare different volumes of different balls. Of course, having a notion of distance simply means you need a metric space. I mean, that's also not very surprising. Now, and what's going to happen that the way that we're going to measure the volume of the ball is going to be related to probability measures. And I'll make this more precise in the next slide. And then once we have probability measures, right, as sort of volumes of our balls, we are going to compare these volumes using the optimal transport distance or Wasserstein distance of order 1. Now, together, this led Jan Ollivier in 2009 to come up with this definition of curvature. So you take a metric space. I mean, it has to be Polish, but that's fine. You take your metric space, And then at every point in your space, you're going to put a probability measure. So every point in your space is endowed with a probability measure. And then if you take 2 points in the space, then the Ollivier curvature between those 2 points is defined as 1 minus, this is the Wasserstein metric, or the Wasserstein distance between the 2 probability measures at those 2 points divided by their distance. Now, for those of you that just maybe don't know or don't remember what the Wasserstein distance metric is, it's this. So the Wasserstein metric between 2 probability measures is just, you look at a joint probability measure and you integrate out the distance over this joint probability measure, and then you take the infimum over all joint probability measures such that the marginals correspond to mu1 and mu2. And this is a very nice metric. However, if you want to actually compute it, right, it's sometimes very difficult because you basically have to solve this optimization problem. But luckily, in this case, we have sort of a very nice alternative representation known as the Convergence-Rubinstein duality, where you can show that this is the same as, instead of taking an infimum over joint distributions, you take a supremum over Lipschitz-1 functions of the differences of the integrals of these Lipschitz-1 functions. Now that's very nice, because what it means is that if you give me any joint probability measure with the right marginals and any Lipschitz-1 functions, I have an upper and a lower bound on my Wasserstein metric. And so if I want to compute the actual Wasserstein metric, and I believe I know the right, I believe I have found the right joint probability distribution, I just have to find a corresponding Lipschitz-1 function that gives me the matching lower bound. And this is often in practice how we actually prove these things. All right. Okay, good. So, okay, here's a formula. This is the formula again. So it's a formula for curvature. Now, the thing is, right, I can show you any formula and say that is a formula for curvature, right? It doesn't say if it's a good formula, right? So let's first do sort of a sanity check, right? So does this formula satisfy this intuition about the changing of volumes of balls, right? So let's just take some Euclidean space. We take 2 points in it, x and y. And now at x, I'm going to look at the measure, which is just a uniform measure on the ball of radius epsilon. And at y, I'm going to put a uniform measure on the ball of radius epsilon prime. Now, if epsilon and epsilon prime are equal, then it's very easy to show that the Wasserstein metric between these 2 measures is just equal to their distance between the 2 points, and hence this curvature is going to be 0. So equal volume, 0 curvature. If epsilon prime is larger, then you can compute that the Wasserstein metric is actually strictly bigger than the distance, and that gives you negative curvature. And the other way around is you can compute that if epsilon prime is smaller, then you actually get positive curvature. And so, I mean, equal volume, 0 curvature. If one of them is bigger, then you get negative curvature. If one of them is smaller, then you get this positive curvature. I mean, this is at least sort of a sanity check, right? If this wasn't true, then I mean, this formula was really just crap. But it's not sufficient, right? So, okay, it satisfies the sanity check, but it doesn't tell you anything about, does it actually measure anything that is related to actual curvature, right? So this is what you can ask, right? Is this formula even related to curvature in the slightest? And actually turns out that on smooth Riemannian manifolds, it actually is. So what you can do is you can take some smooth, complete, n-dimensional Riemannian manifolds, and now you consider the following. Take 2 points, at distance delta. And now at every point in this manifold, we're going to put a random walk, which is just a uniform measure on a ball of radius epsilon. These epsilons are now the same, right? But this lives in some manifold. And then what Jan Ollivier already showed is that if you now compute this Ollivier-Ricci curvature based on these random walks, then you need to rescale it. So you need to multiply it by a constant that depends on the dimension, and then rescale it by the distance squared. And then if you take both the distance and the radii of your measures to go to 0, then this thing converges to the Ricci curvature in the direction, I forgot to say here, this is in the direction of some factor v. And this makes sense, right? Because curvature is a local property. So if I really want to capture curvature, right, I need to sort of look at smaller and smaller neighborhoods. So the fact that my epsilon and delta need to go to 0, that is, I mean, you can't do better than that. But I mean, this is a very nice result because it basically says that in some way, right, indeed, this abstract notion of curvature, at least in the case of smooth Riemannian manifolds, actually properly measures Ricci curvature. So once we found this result, we were very happy, right? Because this notion of Ollivier-Ricci curvature can be applied to any metric space, so we can apply it to graphs. All right. So how do we do that? Well, so we have a graph. So we need to turn this graph into a metric space, first of all. So now the classical thing to do is to consider the shortest path metric on the graph. So it's just any 2 points. You look at the shortest path between the 2 points, and that's going to be the distance. If 2 points are not connected, you put it at infinity. That's a very classical way to make your graph into a metric space. And then you have to pick your probability measures. And a very classical choice here is to just put the uniform measure on the neighbors of nodes. So every node is going to put sort of 1 over its degree measure all of its neighbors. So you can also think of this is basically the probability measure that is associated to a standard random walk in your graph. Okay, so you have your graph, you turn it into a metric space, you have your probability measure, so then you can compute Ollivier-Ricci curvature. And this actually has been done, there are lots of research that actually used this setting, and it's shown that you can use this to actually study robustness of networks, so robustness versus attacks, different types of attacks. You can, in general, analyze stability of networks. It turns out that this notion of Ollivier-Ricci curvature actually is very related to stability of your networks when you start removing edges or nodes. And for instance, people have studied stability of financial networks, brain networks. You can also do community detection if that rings a bell. But you can also find bottlenecks in graphs. So you can use sort of curvature to identify sort of which nodes or which edges are actually bottlenecks for diffusion processes. And all of that has to do at a very sort of deep level that this notion of Ollivier-Ricci curvature, and in particular the fact that we use the Wasserstein distance, relates this to things like heat equations. So you actually this curvature tells you something about how easy it is to diffuse over certain edges. That's actually very nice, right? So we have a notion of discrete curvature. We can apply to graphs in this setting, and people have been using it successfully, right? So, okay, great. All right. So here's the setting again. Okay, good. So what about this question? Okay, can we now use this setting and just compute Ollivier-Ricci curvature for 2 nodes and actually recover some information of the underlying geometry? The answer is no. And I mean, there's a very simple reason for this, and that is that in most of the cases, right, what people do when they compute this curvature, they compute the curvature for 2 neighbors. So just 2 nodes that share an edge. And in that case, of course, the distance is just going to be 1. So we're just computing 1 minus the Wasserstein distance. And you can then very easily show, and this was done by Joost and Liu, that in this setting, this curvature is just bounded by -2 and 1. So 1 is obtained asymptotically for complete graphs, and -2 comes from trees. But I mean, this just means that you can never hope to extract actually information about the true Ricci curvature, right? If I just take a manifold of say curvature 2 or curvature -4, right, I'm not going to be able to do it. Okay, so then are we lost? No, we are not, because I mean, there are some very specific choices that have been made when people study this type of thing. So in particular, the choice of looking at direct neighbors. So we might just not do it. We might just not look at direct neighbors, but neighbors that are a certain distance away from each other. And there are lots of other knots that we can turn. So for example, we can take a different metric on our graph instead of the shortest path distance. Or we can just also change the probability measures at every node, right? So there are different things that we can tune to figure out, right, what is the right setting in which we can actually recover curvature. And that's what I want to show you now. So how do we tune this, right? So what is the right setting to consider? And here, what we really want to do is we want to stay as close to what works in the continuous setting. So in the continuous setting, right, where actually you can recover the curvature, you have 2 points there at the distance delta, and then there's a measure at the distance epsilon. So you have sort of 2 different types of sort of distances. One is how far nodes are apart, and the other is where I do my uniform probability measure. So what we're going to do is instead of looking at nodes that are neighbors, we're going to look at nodes that are not direct neighbors. So there's a certain path between them. And then we have to put some metric on our graph. And in general, we're going to consider a class of metrics that are weighted shortest path metrics. So we're going to consider our graph where the edges have some non-negative weight. So every edge gets a non-negative weight. And then instead of looking at the shortest path distance, we look at the shortest weighted path distance. So for all paths, we compute the sum of the weights and we pick the one that has the smallest sum. And in particular, if all weights are 1, you just get the shortest path distance back. But this is a more general class of metrics to consider. And then instead of looking at probability measures that only look at the direct neighbors, we're going to look at probability measures that look at neighbors that are further away. So in particular, there will be some delta And then we define just a graph ball. So these are all points that are distance at most delta away from X in this weighted shortest path metric. And then we're just going to consider the uniform distribution on the nodes in that ball. Right, so I mean, this starts looking a bit more like the continuous setting, right? And now the question is, can you actually find sort of the right weights to put on your edges and maybe the right sort of delta to actually prove that you can recover Ricci curvature? So this is the setting in which we're going to compute Ollivier-Ricci curvature. Now I just need to tell you the type of random graphs that we're going to sort of compute this on. So these will be random graphs from Riemannian manifolds. So we're going to take a nice manifold. In particular here, we're going to pick it to be compact, orientable, smooth. Compact is not necessary, right? Because it's a local property. So, right, if I just make sure that I look at the graph on a smaller and smaller piece of my manifold, it all works. But just for now, you just think of some compact, orientable, smooth manifold. It makes everything nicer. We're going to take the number of nodes. That's going to be, we take those to infinity. And then there are two other parameters. There's a connection radius, epsilon will go to 0 as n goes to infinity. And then there's this measure radius, delta, that also goes to 0 as n goes to infinity. So what we do is we have our nice manifold, and we're going to fix a root node, right? We need to compute Ollivier-Ricci curvature for two nodes. So we're first going to fix the root node x together with a unit vector v. And then we're going to walk in the direction of v for distance delta n, and we're going to put another node there, yn. And then we're going to compute Ollivier-Ricci curvature for x and yn, and we're going to see what happens as n goes to infinity. So please note that as n goes to infinity, yn gets closer and closer to x. Now, once we have fixed these two nodes, we're going to put the other nodes according to a Poisson point process. If you don't know what that is, just think of n points sampled uniformly at random. And then once all those points are there, we're going to just simply connect any pair of 2 points if their distance in the manifold, their manifold distance is less than this epsilon n. So sprinkle uniform points in your manifold, connect them if their distance less than epsilon n, okay, and you have these two specific points. And then somebody gives you this graph, and now you compute this, you try to compute Ollivier-Ricci curvature and see if you can recover the curvature of the manifold at x in the direction of v. And it turns out we can. So there are different settings in which we can do this. So the first setting is where we have some general n-dimensional manifold, which is nice enough. We pick some specific parameterization of our epsilon n and delta n. That doesn't really matter, but it's just to control both a logarithmic type of scaling and an inverse polynomial scaling of these things. And then as weights in this setting, as a weight, we're going to, for every edge, we're going to put the weight to be equal to the distance in the manifold that the edge actually crosses. So those are weights, non-negative weights. And then we're going to take as a metric our shortest weighted path with respect to these weights. And then we can prove that indeed, if you take Ollivier-Ricci curvature of these 2 points and you do the same type of normalization, so you have to multiply by indeed this constant depending on the dimension, normalize by the distance between x and yn squared, and then as n goes to infinity, that converges to the Ricci curvature. Now here, this convergence is in probabilistic terms, this is known as convergence in expectation, but it's just convergence in the L1 norm, right? This is how you can think of this. That's actually quite good convergence that we get. So, I mean, there are some conditions on these parameters that we picked, and in particular, I mean, we have exact expressions. I don't want to populate the slide with them, but basically what they mean is that this delta n, which is this radius on which the random, on which our probability measures lives, that needs to be at least as big as the connection radius. Preferably, the more we see compared to the connection radius, the better the convergence is. And there are different settings that we consider here. So one is where we can take epsilon and delta to be equal in terms of this, and we get graphs where the average degree scales up to some logarithmic terms and to the 2/3. So these are graphs that are quite dense. So the average degree diverges polynomially. We can also go to under these conditions, we can also go all the way to almost sparse graphs, where now we can construct graphs where actually the average degree only scales logarithmically. So they're not completely sparse, but I mean, the average degree is only logarithmically divergent. So I mean, that's already nice, right? So this is quite general. So these conditions here are actually quite general. It allows us to do it for many different types of graphs. But I am cheating here. And I'm actually cheating a lot, because I am actually already encoding geometric information in my graph, right? So this is, yeah. So somebody gave me a graph, but they didn't only give me the graph. They actually, for every edge, said, okay, this is the actual distance between these two nodes. I mean, this is quite cheating. This was the first result we got, but of course we understood that this sort of cheats, and we don't want that, right? We don't want any manifold information. The next question is, okay, can we get rid of that? Okay, so how do you get rid of this? Well, okay, so let's look at the point x and y, and there's a path between them. Now, I mean, in the previous setting, every edge had as a weight just the distance between these 2 points here, right, in the manifold. And we want to get rid of this. Okay, so what we do know is that in our graph, right, if these nodes are connected, then this node must be at distance at most epsilon n from x. And the same for this node compared to that node. So, okay, so you might think, okay, if I put epsilon n as a weight on every edge, right, then maybe in some way, right, if I just compute the shortest path distance for these weights, which is just epsilon n times the actual shortest path distance, you might think that that might actually be a reasonable approximation of the actual distance in the manifold. It's of course never true for direct neighbors, but maybe if x and y are reasonably far apart, you sort of average out all of the little problems here. And actually it turns out that in the Diaz and co-authors in 2016, they actually proved that, yes, this is the case. So they proved that for epsilon being sufficiently sort of going to zero, not too fast, that indeed epsilon n times shortest path distance equals the distance in, okay, that it holds for x and y not too close, but that's fine. It does only, their result is only true for two-dimensional Euclidean space. Okay, but again, curvature is a local property. So if I can do it for two-dimensional Euclidean space, I just wait until everything is short enough. I have move everything to the tangent space. I do whatever I want to do there, map it back. And if this exponential mapping back and forth doesn't create too much errors, then I might still hope that I can do something here. And I mean, the two here is really, they also mentioned in this paper that this two here, I mean, they believe this to be true for any dimension. It's just that if you want to do it for high dimensions, just the number of administration, right? The administration level of the math becomes sort of very tedious. So they said, we're not doing this. But it is expected to also be true for higher dimension. But that means that we can now try to get results that don't cheat. And for that, what we need to do is we need to just consider two-dimensional manifolds. So two-dimensional, smooth, nice manifolds. Now, again, the same parameterization of our connection radius and this measure radius. And now, as I said, right, so we're going to put weight epsilon n at every edge. So we're just going to compute epsilon n times shortest path metric. And then we can prove that in this setting, you still get the same type of results. Yeah, so epsilon is the radius at which nodes are connected, and delta n is the distance between x and y, and it's also the radius at which my random measures are acting. And in particular, I mean, maybe this answers your question. So there's some conditions, and these conditions, they're stronger conditions, right? I mean, this is not surprisingly, we need some stronger condition. In particular, we need conditions that say that epsilon n goes to zero much faster than delta n to the third. So you really have these two types of scaling. There's this local scaling that tells you where nodes are connected, and there's sort of this mesotopic scaling, that's this delta n, and you really need this delta n to be much, sort of to cover much more of your graph than your neighbors. But I mean, still you can prove this, and the nice thing is that, okay, you can't go all the way down. These conditions don't allow you to go all the way down to logarithmic average degree, but they do allow you to go down to any small polynomial for any epsilon strictly bigger than zero. It's not as good as the previous setting, but it's still, I mean, nice. And here we're actually not using any manifold distance at all. So this is really, it's a discrete structure. We have no known knowledge about the manifold distance. We just compute this, and asymptotically we recover the Ricci curve. So we were very excited about this. The physicists were even more excited. They usually are in this case. So, but the question now is that, okay, we know that this thing converges to the Ricci curvature. That's fine. But if you really want to do sort of applications with this, you have to ask the question, well, how fast is this convergence, right? So how fast? Okay. Now, and then, I mean, then we are in trouble, right? Because our proof techniques, right, they don't give you anything that is better than some logarithmic speed. That's just because of how we prove things. So, so then we said, okay, let's just do simulations, right? Let's do numerical experiments and see how fast this convergence actually is. And it turns out that in reality, it's actually quite fast. So here we stick to two-dimensional compact Riemannian manifolds of three different types of signatures. So the torus for curvature 0, the sphere for curvature 1, and for the hyperbolic manifold, we picked the Boltzmann surface. I also felt very sort of ashamed that I had slides and I was not using the blackboard. So now allow me to use the blackboard. So what is the Boltzmann surface? Well, very simply put, you take an octagon in hyperbolic space. And you identify, basically you identify these, and this is 4. You just identify these two different things. This gives you a compact Riemannian manifold of genus 2. It's called the Boltzmann surface. So we use this one to compute actually or to do the computations for the negative curvature case. What was actually interesting that what we found out is when we were actually trying to do this, it turns out that not that much was known about this manifold. So for instance, people didn't know what the diameter of this manifold was. So actually after this, one of my collaborators together with his PhD student, they actually started sitting down and they actually were able to compute the diameter of this manifold. And they were actually also able to construct ways of effectively computing distances on these types of manifolds. So not just the Boltzmann surface, but any manifold that is constructed in a way like this. It was very surprising for us because we had lots of difficulty actually computing the distance because there was no actually known sort of provable way of doing it. So we contacted lots of experts in Riemannian geometry and said, yeah, whatever you're explaining to us, that should work, but we don't have a proof for this. Okay. So, but how fast does it go? In reality, it actually goes quite fast. So here are simulations. So this is the size of the graph. So we start here, the picture is just starting at 10 to the 2.5, goes to 10 to the 5. So this is about 10,000 nodes. That is, I mean, that's not much. I mean, also, if you think about how large your graphs would be that, for instance, these theoretical physicists would work with, they are much larger than this. And what you can see here is that for the Boltzmann surface, right, this is the yellow line, this is the line for the sphere, and this is the line for the torus. You can already see that already at about 10,000 nodes, these curvature estimates are actually, these Ollivier-Ricci curvature estimates are already very good, which was very surprising for us. What was even more surprising is when we extended our simulations beyond what we could prove. So as I said, right, we can prove these convergence for, in one case, for average degree diverging logarithmically, in the other diverging polynomially with as small parameters as possible. But we could never prove it for actual sparse graphs where the average degree converges to a constant. So we said, okay, we can't prove it at this point, but should it even be true? So then we did simulations where we picked these types of parameters. And these are settings where the graphs that we generate are actually sparse. So the average degree converges to a constant. We then did the simulations, and then miraculously, the simulations are telling us that also in this case, it should still work. Which is somehow very surprising because at least in the proof techniques that we used, we really make use of the fact that as n goes to infinity, you get more and more points in your ball, right? So you get more and more information about your actual manifold within this little ball. And if your graph is sparse, then I mean the number of nodes in this connection radius is going to be fixed. So somehow there's something going on here that at least our current proof techniques are not able to extract. So this is one of the still open problems in how to actually prove this result here. And convergence is still quite fast. All right, so then I'm almost out of time. So let me just end with some final words. So I've been talking a lot about using this Ollivier-Ricci curvature to estimate the curvature of my manifold when I'm in the setting that my random graph is generated on a manifold. I mean, that is nice if you want to do this. But actually, the real thing is really that this notion of Ollivier-Ricci curvature actually provides you with a very versatile framework to study geometric aspects of any type of discrete structures. Right? So you only need a metric space and some probability measures that you can pick yourself. And then you can start studying geometric aspects using this Ollivier-Ricci curvature. So for example, you might be interested, for instance, maybe doing it on Cayley graphs associated to groups, or maybe just doing it at the group level where you have some group with some associated metric. Now, of course, this is not the only discrete notion of curvature. There are lots of other versions out there. So there's what is known as Forman-Ricci curvature, which is basically defined in terms of simplicial complexes. There's also some what is sometimes called empirical or heuristic sectional curvature. It has to do with Has to do with parallelogram rules in different settings. And finally, there's what is known as Bakke-Emery curvature. That only gives you curvature bounds, but it is very closely related to graph Laplacians and heat equations. So, but for all of these curvatures, right, it's not known if they actually can recover actual Ricci curvature. So at this point, Ollivier-Ricci curvature is the only one for which we know that it works. All right, and so now, of course, now still the question is, well, does anybody have an application for this? So we can sort of finish the final A. I probably expect, I was thinking about it, but maybe somebody has something about this we can talk after. But for now, I would like to thank my collaborators. If you're interested, there are 2 papers on this. One is the math paper where we do all the proofs. The other is a paper in Physical Review E where these simulations are there, and there's also more of an elaboration on how this is related to this quantum gravity type of problem. So if you're interested in this test. And with that, I want to thank you for your attention, and I'll be happy to answer any questions.